All right, good morning, Kim 3150. I wanted to take a minute to go through problem 1.24 from England Read, which we looked at in class yesterday. So let me start by reading this problem aloud. When Julius Caesar expired, his last exhalation had a volume of 450 centimeters cubed and contained 1 mole percent of argon. Assume that the temperature was 300 Kelvin and the pressure was 1 atmosphere at the location of his demise. Assume further that T has the same value throughout the Earth's atmosphere, so it's 300 Kelvin everywhere in the Earth's atmosphere. If all of his exhaled argon atoms are now uniformly distributed throughout the atmosphere, how many inhalations of 450 centimeters cubed must we make to inhale one of the argon atoms exhaled in Caesar's last breath? Assume that the radius of the Earth is 6.37 times 10 to the 6 meters, and you can calculate the number of the argon atoms in the atmosphere in a simplified geometry of a plane of area equal to that of the Earth's surface. See problem 120 for the dependence of the barometric pressure and the composition of air on the height above the Earth's surface. Okay, so this is kind of a cool problem, but it's a little bit complicated. So let me tell you first my approach, which is down here. So you can see the first step is to actually calculate the fraction of argon atoms in the atmosphere that came from Caesar's last breath relative to the total number of argon atoms in the atmosphere. So we can probably see right away that we can actually calculate the number of argon atoms from Caesar's last breath. Right, that's basically going to be rearranging the ideal gas law to have N argon atoms from Caesar coming from P of argon times V of Caesar's last breath over R T. Okay, so we can actually calculate that pretty readily, but what's trickier is to actually calculate the total number of argon atoms in the atmosphere. And so we'll talk about that in just a minute. Okay, so then once you have this fraction of number of argon atoms that came from Caesar's last breath to the total number of argon atoms in the atmosphere, what you can do is calculate the actual number of argon atoms in a typical breath that you might take of 450 centimeters cubed, and find out from that breath how many argon atoms came from Caesar's last breath. And that's basically going to be the fraction calculated in A multiplied by the total number of argon atoms in a typical breath. Okay, so that gives you in a typical breath the number of argon atoms that come from Caesar's last breath, and what is really asked for is how many breaths do I have to take to get exactly 1. So that number is actually just going to be the reciprocal of the number of argon atoms that come from Caesar's last breath. So if in B that number that we get, the fraction times number of total argon atoms in a single breath, if that number is less than 1, then we'll need more than 1 breath before we get to 1 atom. If that number is actually larger than 1, then we'll need less than 1 breath. Okay, so that's the overall strategy. And I think, like I said, calculating the number of argon atoms in Caesar's last breath is pretty straightforward, but calculating the total number of argon atoms, period, is a little bit trickier. So let me start by telling you how I set up the problem, and then what we'll do is we'll pause to make a little bit more room on the board and work towards the final solution. So, all right. So this little bit about the simplified geometry, okay, that's a little bit confusing. So the idea, as I see it, is that rather than thinking of the atmosphere as being like a spherical shell, what we'll actually think about it as, which is what the atmosphere really is, we'll actually just model it as a cylinder. Okay, so then the base of the cylinder has the area of the Earth's surface area. And how do we get the Earth's surface area? Well, we're given the radius of the Earth. So that's 6.37 times 10 to the 6 meters. So what's the area? It's just this number squared times pi. So this turns out to be the area of the surface of the Earth. Okay, and so then what we will take, I just realized that I did that wrong. So let's correct that number because that's not the surface area of a sphere. So the surface area of a sphere is 4 pi r squared. This number is just pi r squared. So we actually need to multiply that number by 4. So that becomes actually 5.08 times 10 to the 14th meters squared is the surface area of the Earth. And so then we'll imagine that the base of our cylinder of the atmosphere is going to have that area. And then, the atmosphere can go from the surface of the Earth up and up and up along this coordinate, which we're going to call z. And so how do we know how long to make z? Well, that's an excellent question. So you could, look up a number, but in fact, what we will realize is that they refer us to a different problem in which the pressure of the atmosphere is given as a function of distance from the surface of the Earth. And what you find out is that, in fact, the pressure decays exponentially as you move further and further from the surface of the Earth. So if we get far enough out along z, the pressure is going to approach 0. So we'll use that fact. We'll basically let z go all the way to infinity. And when z goes to infinity, the pressure is going to go to 0. And that will be good enough to approximate the boundary of our atmosphere. In fact, that's probably how we should really do it. Okay. So then the final thing to realize is that, okay, if the pressure were constant throughout the atmosphere, meaning that the pressure at the surface of the Earth were exactly the same at the edge of the atmosphere, then all we would need to do to calculate the total number of moles is to take that constant pressure, multiply it by the volume of the atmosphere, and divide by RT. Right? That would be our rearrangement of the ideal gas law. But we can't actually do that in that case because our pressure is actually changing as a function of distance. So then what we have to realize is that we can define a little differential element of number of argon moles, which has got to be equal to, and that's going to be a function of z, the distance from the surface of the Earth, and that's going to be equal to the pressure of argon as a function of the distance from the surface of the Earth times the surface area of the Earth times our little differential unit of length away from the surface of the Earth, which we'll call dz. So this whole thing divided by RT will be our little differential element of number. And then if we want to actually get the total number of argon atoms, what we need to do is integrate this expression from the surface of the Earth until the edge of the atmosphere. And like I said before, what we'll do is we'll make the surface of the Earth equal z equals 0, and the edge of the atmosphere is going to be z equals infinity. So we'll see that in just a minute after I pause and get some room on the board. But the very last thing that I want to do in this little section of the video is to convince you that this expression makes sense from a dimensional point of view. So we'll do a little dimensionality check to make sure this works. Okay. So I'll remind you that the on the left-hand side are differential in number of argon atoms that has dimensions of n of number. All right, pressure of argon has dimensions of mass times inverse length times inverse time squared. Area, surface area of the Earth, has dimensions of length squared. dz, our differential unit of length away from the surface of the Earth, has dimensions of length. And then R, the gas constant, has dimensions of mass times length squared times inverse time squared times inverse temperature times inverse number. I can't remember if I already said T, but temperature has dimensions of temperature. So our left-hand side's definitely got dimensions of number, which makes sense because we're talking about number of moles of atoms. So I'm going to put number on the left-hand side, and then I'm going to express P in terms of its fundamental dimensions, mass, length inverse, inverse time squared, area in terms of its fundamental dimensions, length squared, dz in terms of its fundamental dimensions, L, R in terms of its fundamental dimensions, mass, length squared, inverse time squared, inverse temperature, inverse number, and then temperature is temperature. So let's just make sure that these units, these dimensions, work out to be number on the right-hand side as well. So I'm going to start with temperature. I've got T to the 1 and a T to the minus 1 here, so those go away. I'm going to look next at length. So I've got length to the minus 1 here and length to the 1 here, so those cancel. I've got length squared here, length squared here, so those cancel. I've got T to the minus 2 here, T to the minus 2 here, so those cancel. M here, M there, those cancel. All I'm left with is 1 over n to the minus 1, right? So in fact, the right-hand side also ultimately has dimensions of n. So left-hand side is n, right-hand side is n. Dimensionally, this thing makes sense. Okay, so the next thing that we're going to do is to continue the work for part A. We're going to calculate the total number of argon atoms in the atmosphere. So I'm going to post that as a second video so that I can reorganize the board. Okay.